In this video, we are going to explore local in much more detail. We're going to explore the formal syntax rules of local, the idea of lexical scoping, evaluation rules of local, and the benefits of using local. All right. So here are the formal syntax rules for local. It starts off with the name local, and then a set of square braces or parentheses. It doesn't matter, just be consistent. I choose square braces for some more visual clarity, right? And then after that comes the body of the local. So inside this is the definitions, right? This is where you can write your defines and etc., right? And here is the expression body. And you can use the definitions in the expressions we hear, right? The definitions are only valid in the expression body here, right? So let me show you what I mean, right? So local and then square brace, you can define A to be 1, and then define another variable B to be 2, and then we can use those inside the body over here, right, after the square braces here. So plus AB, you can guess what this whole thing will produce. It will produce 3, right? Not only can you define variables, right, you can define functions. So define g of x is going to be plus x of 5, right? And you can use this g inside the body over here, expression body. But you don't have to. I just run this code. Nothing's going to happen. It just doesn't use this g, right? This g is still inside this local block. It can only be used inside this local block, right? But, you know, I'm not using it, so it's cool. I could use it like, so I'll just use it here. So g of 0. So this would be 5 plus 2 plus 1. So I should get 8. All right? If I try to use this g or any of these variables outside this local, right, then I'm going to get an error, right? If I type in a, run, right, this variable is not defined. If I try to use b is also inside this local, right? If I hover over it, it's not going to draw the arrow, right? So b is not defined, and g is also not defined, right? It's only valid inside this block, right? This scope. It's similar to function scopes, right? Define f of x, and then x plus 1 plus x1, right? This x is only valid inside this function. If I try to use an x outside this function, it's going to say, hey, I can't find an x, right? But f of x does have a parameter x that it can use. So again, we can't use variables inside functions. All right. And that is the formal definitions of local, right? The formal syntax rules of local. Some errors people make is they do something like local, and then for each variable, like a1, right? For each one, they're going to put another square brace, right? Define b2, right? This is wrong, right? There's only one set of square braces, and then you delimit the more defines with a new line, all right? Another mistake people can make is that this, right, this last expression has to be an expression, has to produce a value, right? So if you make it a statement, right, let me copy and paste this down, right? This is the definitions, and this is the expression body, right? If I do a define here, and then do, you know, z of 1, right? It's going to say, hey, right, this has to be an expression. It can't be a statement. All right. So that is the formal syntax rules for local. So next, let's move on to the idea of lexicoscoping. So lexicoscoping determines how variables resolve into values when inside local blocks or function blocks. So it's better if I show you right here, right? So here in global scope, we call it global scope because this p can be accessed by anyone inside the inner scopes, right? Inside function scope or local scope. It's way out here. So p is bound to the string n, and we have a local block, which also defines a p that is bound to the string bob, and a function greet that string appends n, the parameter gets hello, and then p is going to be resolved to the nearest p, right? The outer p here in the global scope is being shadowed by this local p, right? So it's going to get the variable from the closest position in the source code right over here, right? It's not going to get it from and over here. If I were to comment out this bob, right, then it would look to the global scope for p because it can't find it inside this local scope. So it's going to keep looking outer, up, and up until it can find the variable it needs. If it can't find the variable it needs, of course, then you can guess what that means. We just get an error, right? P is not defined. I need a p, right? Greet needs a p to do its job, right? So that is lexicoscoping in a nutshell. So here is a good step-by-step process to draw out and visualize where functions and variables are valid inside scopes, all right? So I'm gonna give myself some space here because we're going to be drawing over this code. Gonna take a screenshot and copy and paste it into a notepad over here. So how this works is that Racket is going to go over your code line by line, right? And whenever it encounters a local, it's going to draw a box around it, or a function, it's going to draw a box around it, right? With the exception of global scope. So let's just do that, right? So the program starts and Racket is going to go line by line and it's going to record things in the global scope, right? So it's going to draw a box for global scope. So global records a variable p, right? So let's go line by line recording things it encounters, right? So global has a variable p out here, right? And then when we hit a local, we have to draw a box around that, right? So let's draw a box around the local, right? And it's going to record the variables inside the local, right? So local, this local scope, right, has a variable p, a function greet, all right? And then when it encounters a function, right, again, a box gets drawn. So let's make this one yellow. So this greet is also going to be a scope, right? It's going to be a function scope, right? Function scope, right? And we're kind of running out of space here. So I'm going to put it here. So this function scope also defines a variable n, right? A parameter n, right? But it's a variable nonetheless. And then it's going to record an outer reference to p, because this p doesn't exist inside the parameter list, only an n does, right? So we see a greet here, and this greet is inside the local scope, right? Local scope is recording a greet function. That's why we can use it in the body of the local here, right? So the lookup rules are pretty much the same, right? If we encounter a variable that we don't have, we're just going to go look up to the nearest scope, right? So this yellow box, right? Again, greet has a p that it doesn't have in the parameter list. The next nearest scope is the local scope of this local block. And it's going to go grab that, and p is going to be Bob, right? And then if it can't find Bob, right? Imagine this p was commented out, it'll go get Ann, right? So hopefully this gives you a visual intuition of how to diagram out scope contours, right? So here we go, right? So this p can be accessed out here. If I type in p, hit run, we get Ann over here. I can also use p, right? But I can never get this Bob, this variable p Bob from this local, right? It's only valid inside this local. It can't get out, right? So yeah. Also likewise for this function greet, it can't really escape this local block, right? So also if I have another variable, let's make it a function. Let's make it moo xn plus x1, right? This is going to be in the global scope, right? So if I copy and paste, let's just screenshot this and paste it in. So screenshot, where is the copy? Paste this in, right? This one is in the global scope. So global will have a what is it? A function moo, right? So let's get rid of this t, right? So this moo, right, it's only valid like way down here though, right? So if I try to reference moo inside this local block, right, it's not valid until it hits this all the way down here, right? So let me show you guys, right? If I try to use, you know, this moo produces a 1, this moo produces a number. So let's do this. I'm going to do a string append here. So string append. I'm going to turn this number into a number to string. So number arrow string moo of 1. All right, so that should be 2, right? Moo of 1 is 2. I have to run this code. Moo is not defined to run this. Just give me an error. Moo is used before its definition here, right? So this has to be moved up here in order for the lookup to happen, right? So I get hello Bob 2, right? So yeah, walking line by line and then recording things like so, right? And that is how you should think about local. You walk line by line and then you draw a box whenever you hit a local or function scope, and you record in this specific order, right? You record p, local scope, record another p inside this local scope. The function greet records the variable n and the outer reference p, And then we're back outside this local. We have a moo, and this function moo is only valid from this point downwards, right? From this point downwards, right? It can't be used inside this local unless you moved it above the local, right? Like so. So that is how you should think about local blocks. So next, let's move on to the evaluation rules of local, right? The step-by-step process of how local gets evaluated into a value. So I have some code here, right? We have a global variable b bound to 6, and we have a local block inside this addition block, all right? So how do you expect these variables to get resolved, right? Pause the video. Without running this code, right, you can plug in these values here. Try to guess what the final answer of this will be, right? This whole thing is going to produce a number, all right? Spoilers in 3, 2, and 1. All right, I'm going to assume that you guys took a good swing at it. Now let's go over it together. So let's evaluate this line by line. All right, so this first b becomes 6 because it's in the global scope, right? So this b resolves to 6, right? Next iteration, right? All these have to be numbers in order for plus to do its job, right? So how does this local get evaluated? Well, 3 things are going to happen. First comes renaming, then lifting, then the local goes away. So let me show you guys this in live action, right? So Racket is going to rename all the definitions inside the local over here to a globally unique name. So we're going to do b_0. Internally, Racket, renames it to a bunch of jitterish that will never ever be used. We'll use b0 for now, just for simplicity's sake, right? So b0, right? So it renames for rename, right? Then lift. So all these local definitions will get lifted up to global scope, right? It has a unique name, so it's never going to clash with any variables, right? And then remove local, right? The local gets removed, right? So like so, right? And now we have a BSL program, right? It's no longer an ISL program. It's a BSL program, right? It's similar to if, right? So if true, the string moo and then the string, wolf, right? The if goes away, right? It just resolves to the strings over here, right? Like so. So that's what I mean when I say the local goes away after we do the lifting, right? So first, b inside this definition of local gets renamed globally to a unique variable name, b0. Then it gets lifted to global scope, right? Lifted. And then the local goes away. And then now we're left with an ISL program that we can resolve all the variables. So this b0 is the variable that we just lifted to global scope, which is 2 now. So this is 2 and 2. And then we can evaluate that to 4, right? We just get rid of these. 4, right? And then this b, right, gets resolved to global 6, right? You can right click and then jump to next bound occurrence, right? It's going to get resolved to this global 6. And now we have a addition expression. 6 plus 4 is 10 plus 6 is 16, right? So there we go. And that is how local gets evaluated. So if you got 16, that is the right answer, right? It's kind of tricky here, right? The speed looks closer to this local block, but it's in the global scope. So it's the nearest scope that matters, right? So yeah, this b down here resolves to 6, not this 2, because this 2 is only valid inside this local block over here. So we can also see this in the stepper, right? So just going to step through this code. All right. So this b resolved to 6, right? Then we hit the local. So you're seeing the renaming and the lifting happen just in one step, right? So let me go to previous, right? Once we hit the local, right, we see a define underscore b02. I didn't write that, right? So here's my code. I didn't define a b_0 in global scope. Racket's going to do that. And then it's going to put that in global scope and then resolve the local, right? The local goes away and then resolve to the global 2 over here. And then like so, right? And then we get the full evaluation to 16. All right. So you might be thinking, right? Hey, right, look at this. It, lifts this local b, comes up with the name b_0. Let's actually think we're clever. Let's define a b0 to be, 9, right? And then run this. Well, we still get 16, right? Pause the answer and try to think about that. Spoilers in 3, 2, and 1. Yes, we will, because it's just going to come up with a unique name, right? This B0 is not referenced everywhere. So let's just go back to the stepper, right? So again, it renamed the inner scopes, right? This B to B0, and then I wrote a B0 right over here just to see if I can trick it. It says the program has changed, so I actually have to close this and then click step again, and then you will see that if I hit next, it made this inner scope, right? This defined B2, it renamed it to B_1 and then bound it to 2, right? So yeah, it's always going to come up with a unique name when it does the renaming and lifting of these local variables here. All right, so now let's move on to our final topic. What are the benefits of using local? All right, so one of which is clarifying readability. So I'm going to copy and paste some code I have here off to the side. So we have a function that calculates the shipping cost of something based on the weight and distance. So it's okay, but why are we adding this 5, right? What does this number mean, right? It has a meaning. What does 0.5 mean and 0.1? We can understand this, if we stare at it hard enough and think about it a lot, but you can imagine this being a lot more complex, right? So instead, what we can do is use local variables to clarify what numbers mean, right? Give a name to these numbers. So 5, right? Why are we adding this 5? Oh, I see. Straight from a glance, so we use local, right? We're defining it to be the base shipping cost, right? And 0.5 is the cost per kilogram, right? So we're actually getting the metrics here. Whereas if you just look at this 0.5, it's like, what is this, right? Is it per pound, per, etc. So we see cost per kilometer, right? And then like so. And then the total cost is the addition of these, like so, right? It's the same thing, just expressed differently, right? So the second version is more longer, but it's a lot more clear. And imagine this is a much more complex program. This is just a very simple formula. You can imagine something, like much longer, much more complicated. And it's not so easy to just look at a one-liner and go, oh, I understand it, right? It's easier if you write the long version and just give things names. So that is one of the benefits of local, clarifying readability. Another benefit of using local is fixing efficiency problems. So I have some code I'm going to copy here. I'm going to paste it here. This is a bad implementation of largest num. So largest num consumes a non-empty list of number and produces a number. It determines the largest number in the given list. So given the list 2, this is the only number in this list, so just produce 2. Given the list 746, produce 7, because 7 is the biggest in this list. Given the list 1932, produce 9, because 9 is the biggest number out of these 4 numbers. So just run this code. Nothing is wrong with this code in that it will find the largest number in the given list. The problem is that it gets really, really slow when the list is long. So let me just show you what I mean, right? So here is calling largest num with a 22 element long list. I'm going to run this. See how long it takes, right? Compared to earlier, it takes a little while, right? How long does it take? Well, if we wrap it around the function time, it will tell us how long in milliseconds, right? So it took roughly 1 second. Hopefully it doesn't lag the recording, but that's how long it's going to take, right? For a 22 element long list. It shouldn't take that long. Computers are really, really fast, right? If we add so this is a 22 element long list. All right. If we just add 4 numbers, let's just see how long it takes, right? This took 1 sec to determine that 9 is the biggest number in this list, right? So this is a 26 element long list. Right, so I'm gonna add 4 numbers, so 8, 4, 1, 7. Right, let's just see how long this takes. Right, I'm gonna comment out this first one. Gonna run this. And let's just see how long it takes just by adding 4 elements, right? 26, 22 elements to just 26 elements. It takes 6.8 seconds, right? This is in milliseconds, by the way. So CPU time, 6.8 seconds, right? 6,807 milliseconds divided that by 1,000, you get seconds, right? So 6.8 seconds to determine the largest number of a 26 element long list. That's not going to fly. Why is this so slow? Well, let's actually look at what largest num does, right? The code motion here, right? So what it does is that it's going to look through every element in the list, right? So here, and it's going to say, hey, are you bigger than the rest of the list, right? So it's going to keep recursively calling itself and check the rest of the numbers here. If it is, then we're done. Just return 7. If it's not, go move on to the next number and do the same motion like so, right? 0 Is 0 bigger than the rest of the list? No. Is 4 bigger than the rest of the list? No. Right, we're going to keep doing that until we get to 9, until 9 is the biggest of the list. So under this execution flow, you would think that, hey, if I put 9 all the way in the beginning, right, and then 9 is bigger than the rest of the elements on the list, it should be faster. And it is. So let me show you how, like, that is an improvement, but, you know, it's not realistic because numbers can really appear anywhere. So if I put this 9 in front, right, it is a little good amount faster, right? We've gone from 1 second to 200 milliseconds, right? So like so. So I'm going to delete it. And let's do the same here, right? This is 26 on the long list. This is the one that takes 6.8 seconds. Let's stick this 9 all the way here, right? So 6.8 seconds, and it's going down to, let's see, 6.1 seconds. So it's still pretty bad, but there's a reason for this, right? The reason is that we're doing 2 recursive calls here in largest num, right? So largest num will call itself, right? And then when it does that recursive call, those 2 are also going to do 2 recursive calls, right? Like so. And it's going to keep going. It's going to keep going, blowing up, right? So it went from 6.8 seconds and then down to 6.1 seconds. It's still pretty bad, right? But let me just put the 9 back to where it was, right? So what you end up here is exponential blowup, right? So it's going to look like this, right? So this function will do 2 recursive calls, and then that function will do 2 recursive calls, right? Those 2 functions will do recursive calls, and then those 2 functions will do 2 recursive calls, and then you end up with exponential blowup, right? It's like if you have a rule in your family, like saying that you must have 2 kids. Well, your 2 kids are going to have 2 kids, and those 2 kids are going to have 2 kids, so you end up with 4. And those 4 kids are going to have 2 kids of their own, so you get 8, and then it just blows up like so, right? After it just blows up really, really fast. So the function to model this is 2 to the power of n, right? So n is going to be the size of the list, and we just plug that in, right? So exponent 2 to the power of 22, right? So determining the largest number of a 22 element long list, which is this case, is 4 million computer operations, right? And for a 23 element list, right, let's just, you know, bump it up by 1, right? It's just 8 million operations. And then if we bump it up to 26, right? This was the one that took 6 seconds, 6.8 seconds, right? It is going to take 67 million operations, right? To compute the 26, the longest of a 26, the biggest number of a 26 element long list, right? So we can fix this with local actually, all right? So what we need to do is we can store computations with local and then use the variable lookup, right? So what we're going to do is go to the nearest spot where we need the local, which is here, right? We can wrap it around here, but really we need it here around this if. So we're going to wrap it in a local. And what we're going to do is we're going to store this larger than rest, right? We're going to store this recursive call so that we don't end up with this exponential blowup of this recursive call, making 2 recursive calls, making 2 recursive calls like so, right? So we're going to do it define here. And then larger than rest is going to be the name of the variable, and then do the recursive call. We have to do the recursive calls, right? There's nothing wrong about doing the recursive calls. We have to do it because we have to go look for the biggest number in the list. The problem is we're doing it for each, you know, exponentially, right? For each recursive call, we're doing it twice, and those 2 are doing twice, those 2 are doing twice. So we store it, make a local, we store it into a variable, and then now we use that variable, and it's just going to look up that computation rather than doing the computation itself, right? So just run this code, right? All the 3 tests do pass, and let's compare how long it takes, right? So I'm going to uncomment this out and run it under this new local implementation and see how long it takes from 1 second to instant, right? It says 0 CPU seconds. So it's not really instant, but it's like, you know, a couple milliseconds, right? 1 to 2 milliseconds or nanoseconds or something, right? What about this 26 element long list, right? It was 6.8 seconds. Remember this one was really, really long? Well, let's just run that independently. I'm going to comment this first test out and like so. Let's see how long it went, right? Virtually none, right? That's just computers, right? They're pretty fast. They could, you know, determine the largest number of a 100 element long list very, very fast, right? This shouldn't be really anything to sweat about. And that is one of the ways you can fix efficiency problems with local. Now, just a word of caution, don't get too obsessed with storing variables for efficiency reasons, all right? It should be for typing reasons, right? So let's say I was tired of typing first of LST here, right? Let's say I had to use this function, this first of LST, like 10 times in this function, right? It's better if you, define it into a variable and then define it to be n1 first of LST and then replace it everywhere first of LST with n1, right? This is a good use of local, right? Because you're reducing typing, you're reducing parentheses and so, right? This is especially going to be the case for structures, but nonetheless, right? Don't do it for efficiency reasons. If you have like an add one, right? Like a +1 or something, plus x plus some number, right? You don't really need to do this in another definition here. Right? You don't have to define a variable for it. You could, but don't do it for efficiency reasons. Do it for readability and typing reasons. Because efficiency, right? This case is pretty rare, right? You do have to be aware of exponential blowup, but we're not going to spend too much time with problems that have this factoring of you have to put this thing in the local to get efficiency gains, right? We only have like 2 problems that have that. So yeah. And last but not least, the final reason to use local is encapsulation. So I'm going to copy and paste some code I have here off to the side. So this concept is kind of familiar, right? So we have the distance formula and it calculates the distance between 2 points. You give it 2 points and it'll give you the distance between them, right? And here is the slope function. So it's rise over run. In this case, it's run over rise because we're storing it in a point to definition and it requires it to be x and y, right? So for example, the point 1, 1, if we want to get to the point 2, 3, we have to add 1 in x. And then for the y to get to 3, we have to add 2, right? So yeah. So both of these have local blocks, and both of them have a delta x and delta y. They don't conflict with each other, right? They're each their own versions, right? Imagine if it wasn't like this, right? Imagine you have to come up with unique variable names for every local variables, right? Inside functions, right? So you can imagine, you would run out of names, right? Frankly, delta x and delta y describe the subtraction of x and y, right? The first x and the second x perfectly. So yeah, this becomes more obvious when we have locals that have functions inside them, right? So I'm going to paste some code down here, right? So here we have a structure plane and structure vehicle, right? And these 2 functions, they calculate the plane speed and vehicle speed, right? So for plane speed, right, this has a local block, it has air resistance, it factors in air resistance. You can imagine this being a long function that grabs data from the sensors, right, about air resistance and lift and etc. And you can imagine vehicle speed being more complicated, right? It has traffic in here, and you can imagine, the road friction, right? If there's ice on the road, right? You can imagine these functions being a lot more complicated. But both of these functions have their own local definitions, and inside their locals is a function called calc speed. They both have their individual versions of calc speed. They don't interfere with one another, right? And you're going to often have this case where you're going to have functions that are only valuable inside the context of implementing the larger function here, right? So imagine if calc speed was moved out here to global scope, right? It's not really useful in the global scope because it needs this closure to this traffic variable, right? It's not defined here, right? Same with, the plane speed, right? You can imagine this being in a plane program, calc speed inside, right? This local, it's only variable inside the definition of plane speed, right? This calc speed, right? It consumes a plane, right? And it closes in the variable air resistance, right? Which is read from like a sensor or something, right? So we stick it in this plane speed rather than the global scope, because not only does this prevent namespace pollution, right? That is, if you put more things in global scope, people will have to come up with different names for stuff all the time. But if you stick it into local scope, right? Someone can define a calc speed if they want, or it's not the best option, but they can have more space, more breathing room for names, right? So that is why we have functions inside local definitions, because it will make it so that no one can call calc speed, right? So generally, you want to limit the scope of functions, right? Functions that are unhelpful and specific to other functions, right? This is a specific function to the plane speed function, right? So they don't pollute the global namespace. For useful functions, right, you want the scope to be wider. That's why you put it in the global scope. So yeah, you can imagine, right, Racket has a bunch of things in the draw library, right, like draw triangle, right? and draw circle, right? Circle, etc. Circle probably has, 5, 10 other functions, right? To use, I don't know, pi or something to calculate, the circle and how to draw it. But you don't really want to know about that. You just want to use circle, right? So it's about providing a good customer experience to people using your code and you in the future, right? So encapsulation is, the final reason. And it's arguably one of the more important reasons, right? Because it allows you to have, variables here with the same names, but they don't conflict with one another. And it allows you to hide functions inside local blocks so that you don't pollute the global namespace. And those are the 3 benefits of using local: clarifying readability, fixing efficiency problems, and encapsulation, right? We're not going to run into efficiency problems too much, so mainly focus on encapsulation and readability. All right? And that is about it for this video, and I will catch you in the next one.